CLion, a cross-platform IDE for C and C++. Download now.
So hi everyone, I'm the CTO of the Audio Squadron Group. We are a professional audio company. We have two main sides to our business. We have our Prism Sound brand, where we make high quality desktop rack-mounted audio interfaces and also large channel count converters for big studios. And on the software side, we have our Traction brand that make a whole bunch of virtual instruments for making weird and wonderful sounds, and a digital audio workstation, which is a kind of multi-track recording, production application. And the engine that powers that, so the data model, the real-time elements, all kind of the low-level stuff, is part of an open source project called Traction Engine that we also license to other companies so they can put their own front-end UI and create effectively a unique app that has the same back-end. So when I'm not programming, I like to do building work. Here's some various stages of a garden office that I built. I like building work because it's actually very similar to programming in that you're solving engineering problems, but it's a lot more physical. It gets me away from the desk, and you can listen to a podcast, bit of music, and just kind of switch off a bit. And you also get something cool physically at the end of it. So this is the result of the office. It's where I'm sat now, and it's where I sit programming every day. And when I finished that, I moved to the front of the house, learnt some new skills like block work, pitch roofing, rendering, and built a porch. And that turned out pretty great as well. So if you want to talk to me at the conference about something that's not programming, power tools, construction, building work, anything like that, I really enjoy. So that's just a little bit about me kind of personally. So back to programming, and a little bit of a caveat. I'm not going to give a sort of introduction to safety and security because I think that's given me quite a lot of times now at conferences. If you do want a good background, I would recommend C++ and Safety by Timur. He's given it a few times over the past few years, so definitely check that out for a kind of base level introduction. But I'm going to really kind of start where this journey began for me. So a few years ago, there was a group of Chromium developers created a report that basically, I'm assuming due to the increase in adoption of Rust, looked at what it might take to add a borrow checker to C++. And they kind of wrote up their results, and the conclusion was not exactly great. It said, however, the language does not lend itself to this, thus memory safety in C++ would need to be achieved through runtime checks. So they basically said it doesn't fit very well. Now, Sean Baxter, the Circle developer, which is a C++ compiler with a whole bunch of language extensions that uses as a sort of invention space and for testing things out to see how the language could be evolved and how ideas pan out, basically said, hold my beer. Now, he went away for some period of time. I'm not sure exactly how long. It was a year or two, something like that. But in the middle of last year, he sort of announced he'd kind of cracked safe C++ with a webinar. And he basically went through how he's applied Rust's safety model in all its different kind of caveats to C++. And for me personally, to be honest, if you want a good introduction around Rust's safety model, watch this webinar because it gives a really good introduction. And because it does it with like C++ syntax, it's really easy to understand. You don't have to know Rust. But for me, the thing that really stuck out was when he got to thread safety, and just the way the ideas and the pieces fit together was something that I hadn't really seen discussed properly. So this is really my experience of taking what he started there, thinking this looks a bit like C++. What if we were just to try and apply these ideas to C++, and then start looking at how these problems are solved in other programming languages, and could they be transferred to C++? So it's basically saying thread safety, will it C++? Now, we're talking about thread safety. We probably want some kind of definition. So what is thread safety? A program is thread safe if it is free from data races. Technically, you want to include deadlocks and like system resources there as well. But as we'll see, if you fix the data races, the others tend to fall out a bit more easily. So therefore, you can define a data race when there are two threads accessing the same memory location when at least one of them is a write. And therefore, it follows that a safe programming language makes it impossible to express data races. So why thread safety? Why is it important? Well, I couldn't find many data points on this, but there was a report by Google last year who tried to categorize each of their CVEs in the wild. And as we can see, thread was only 5.6%, the vast majority in temporal, spatial, and time. So this 5.6% might seem small, but there's a lot of work in C++ being done on those other areas. They're often described as low-hanging fruit. So I think as those issues are fixed, that 5.6 will become bigger. And also, as machines gain more cores, we'll be using more threads just in our normal everyday programming. So we'll probably see more thread-related issues. And this is already evident because things like stood execution, which makes it really easy to run things on different threads, are being added to the standard. And as we'll see through this talk, it's useful looking at threading because things like lifetime and temporal safety are inextricably linked. Often just looking at one, you get gains in the other. The other side of this is that thread-related or data race bugs are really difficult to spot and debug. It's because the problems typically arise long after you've had a data race. So I kind of hypothesize that if only 5.6% of the bugs are thread related, the time spent fixing those bugs is likely much higher. And also, I mentioned this is just one data point. I'm not intimately familiar with Google's code base. I know they do use lots of different languages and use protobuf to communicate between different processes and things like that. So maybe there's a bit of inherent kind of safety going on there. But I do know personally in the audio industry, and I imagine any real-time industry where you have a thread continuously going, or sometimes multiple threads working cooperatively, hundreds of times a second, you're likely to get a lot of thread-related issues. So there are a landscape of languages that all approach this slightly differently. They all fundamentally try to avoid sharing state because we know that's where data races come from. On the left-hand side of this diagram, we have Haskell, which aims to do it through immutability, where essentially every new value is a pure value, and therefore there is no possibility to be able to share state. In the middle, Hilo takes the approach of, yes, we want that kind of immutability, but only on a global scope. On a local scope, we can have mutable values, and that gives us kind of local reasoning, but we still don't have to worry about sharing data in the same way as we do in Haskell. And on the other side, we have Erlang and Elixir that deal with message passing, which aims to kind of reduce the amount space between threads, the contact patch, to a very small area. Now, I'm not going to talk about Haskell because it's, pure value semantic programming, higher order functions, that kind of stuff doesn't fit well to a lot of C++ code. And also Jonathan's given a keynote on that. So watch that for his ideas. And I'm not going to talk about message passing because I think Anthony Williams gave a good talk possibly at this conference last year. So have a look at that for inspiration. We're mainly going to be concerned with the ideas from Rust and Circle, therefore, and also Swift, because I think they map well to C++. And this primarily comes in two parts. We're going to look at the low-level sync and send mechanism, and then a much higher-level actors mechanism later. Now, sync and send are protocols or traits, depending on the language, that essentially have two properties. A sync object can be safely shared between threads, so doesn't have a data race on that object, or it makes it data race free. And then a send object can be safely transferred between threads. So this essentially means that you can pass an object across to another thread, and it won't leave bits of itself dangling that could race. Now, in Swift, this is given to the programmer in terms of the sendable protocol. And this really introduces the notion of isolation boundaries between potential thread execution contexts. Now, objects can pass this isolation boundary only if they conform to the @sendable protocol. And this can be inferred in some cases, like you have structs that have trivial data types, that it can kind of reason that there's no way for that object to be left dangling in the other thread. Syncable objects are really just a special case of sendable objects in Swift. Imagine you had a lock-in resource, which was an object that was guarded by a mutex that got locked every time you wanted to access the object. You would just say that that conformed to the @sendable protocol. There's no separate kind of syncable keyword. And you can see this in Swift code with the @sendable protocol. Here, a thread is being initialized with a block, which is similar to a lambda, and that block has to conform to that sendable protocol. In Rust, it's a similar story, apart from send is called a marker trait, which I guess is similar to a C++ type trait, and it can be inferred if you have pure value semantics, so arithmetic data types that can be copied easily between threads or cross threads really. And because Rust has the borrow checker and borrow semantics, you can share a borrow, which is similar to a const reference, but not a mutable borrow, because if you have a mutable borrow, it means that one thread might change that whilst another thread is reading from it, and therefore a data race. And in Circle, it's basically the same idea, apart from send is called a marker interface, and the syntax is slightly different. Sean kind of sticks with the C++ const t hat, which is the kind of borrow syntax, and then a mutable borrow is just without the const. Now, in the kind of latter third of his webinar, Sean introduced this example where he has a bunch of threads, 15, that each take a function that aim to append and then print out a string. And he shows how this sync and send straight in tandem with the borrow checker avoid you from writing data races. And I thought, well, a lot of this looks like C++ type traits. So what would happen if we just tried to implement this using type traits? So what kind of follows is my investigation, my trying to replicate these ideas, and I've written it up into something called the safe concurrency library. I was going to call it the safe threading library, but it turns out STL is a taken term. And I wrote a bunch of slides to start from first principles, but that takes about an hour to talk about. So I'm going to jump right to the end and just show essentially how it's used. So you effectively, what you're doing with send is constraining arguments to pass on to existing thread constructs. So we just create this wrapper class around an existing std thread and then constrain the arguments that are going to be passed to the invocable. And we're also going to constrain the invocable. We'll see how this kind of plays out in a few slides' time. So we've got these two concepts that are being applied to the arguments. And the concept is just created from a type trait, and the type trait is essentially in two halves. First of all, it checks that the type isn't an L value reference, and it's not a pointer, and that it's not a lambda. Now, lambdas are problematic in C++ because they can effectively capture anything, including pointers, dispointers, and so on. So at this stage, we just have to reject them completely. And this is lambda v, is just the type trait that checks for an object with an overridden call operator. The other part of this deals with being able to construct objects. So if the type is move constructible, then from the type, then we're essentially saying, if you give me an R value reference, I can create a new copy of this in the thread. So that's C++'s best notion of object transference, like lifetime change. And the final bit is that we allow function pointers as long as they're not member function pointers. And the reason we do this is because member function pointers need a this pointer, and a this pointer is just an object pointer. And once you have a pointer, all bets are off, really. They can be aliased elsewhere. And what you get if you do this is essentially a really restrictive set of tests. So plain objects like ints and R value references conform to this send concept. But anything that looks like a pointer or a reference to an arithmetic type or an object like a string is disallowed. And you could kind of reason this out. I know the type trait is a bit weird, and I'm not the best meta programmer, so I'm sure someone could write it a bit more cleanly. But in my head, this is the sort of the flow chart of questions that get asked. Now, the interesting thing about Rust is that it effectively has this additional check at the front that says, is the type a mutable borrow? And if it is, then it rejects it. But if it's a borrow, which again is similar to a const reference, then it says, actually, yes, that can be passed, because if you're only going to read from an object across multiple threads, there's no data race. So just in summary, send in C++ would be no L-value references, no object pointers or lambdas, because these may be referenced outside the thread boundary. They might be aliased. You could have a non-const reference to an object that you then turn into a const reference and then pass to a thread. So we just can't allow those. What we're only allowing is effectively R-value referenced and non-member function pointers, because that's our best way of saying, okay, we're kind of narrowing the boundary of opportunity for data to be shared to be as small as possible. Sync is a bit easier to explain. We define it as a fold over a bunch of arguments, because we can accept any number of arguments to pass to a thread. So we just have to make sure we apply it to all of those. And then we just start by saying, well, no type conforms to the sync trait. But there is one type, atomic, which actually is free from data races. So we say, if the type is an atomic of a T, then actually that does conform to the sync protocol. And again, with a bunch of static asserts, it's quite obvious to see how that falls out. So atomic works. So what types are sync? Well, we just mentioned atomic. That has the unfortunate drawback that it's for trivial types only. Now, there has been an in-flight proposal for this synchronized value class, which wraps a std mutex with an object and then just locks the mutex before you get access to the object. And that has the benefit that it works with any type. Now, I've just created a version of this from the proposal. Unfortunately, it's been around for quite a few years and hasn't made it into the standard yet. But if it does, it will probably look something like this. So remember, you have the mutex and the type, and then you just forward on the arguments when you construct one of these to that type. And then when you want to access it, use this apply function, and you just, it's a free function. It's written like this because you can lock multiple synchronized values and then pass the same apply function to them, and they're all locked at the same time. But effectively, you're just locking the mutex, and then you get a reference to the internal value. And because we know that using one of these is free from data races, we can add our own custom type trait to say, actually, this conforms to the sync trait as well. Now, you could add the check for is sync here at the end, because, in theory, we're saying that, yes, sync objects are also send. But because of the way we've written this in C++, we don't have any way to share a reference or a pointer to a sync object. This check is never really going to be hit, or it's never going to be useful, because we don't have a reference that is actually going to be across two different threads. So instead, what we can do is say, well, the best idea that C++ has that is a shared reference is shared pointer, really. So if we have a shared pointer to a T, and the T conforms to the sync trait, then we're saying, well, that is send as well. Again, slightly complicated, but when you use the code, it makes more sense. So what we're saying is a shared pointer to a atomic is send, and we're saying a shared pointer to a synchronized value is send, but a shared pointer to an int, because the int isn't sync, that's not send, and because a string is not sync, that's not send either. And what that really means is when you try and write code, the compiler will try and force you into using safer constructs. So if I go over this example, first thing it does is says you essentially need a shared pointer to a sync to a string in order to be able to pass this to your threads. And then you need to convert those arguments to R values effectively by creating copies. And then you need to pass a function pointer, effectively a global function pointer that isn't a member function pointer, to your safe thread constructor, and then it will pass all those checks. And of course, you have to mirror those arguments in the entry point function to take a shared pointer to a synchronized value to a string. And then finally, you can use the apply function of the synchronized value, which will lock the mutex, give it a lambda, and then you get a reference to that internal string that you can append to and print it out completely free of data races. So quite a lot there. And immediately we can see a whole bunch of problems with this C++ implementation. Now, imagine this is not a string, which is actually quite a nicely self-contained object. Imagine this is something more like a node. So node's copyable because it is just 2 pointers, but because it contains 2 pointers, those pointers could alias to anything else. So accessing the object could well be a race condition or a data race. The other problem is that you don't often see threads being created like this in C++. It's much more common, at least in my experience, to see passing a lambda with a this pointer and then calling a member function. But remember, the this pointer is just an object pointer. So you've got no guarantees that that isn't being data raced by another thread somewhere, and you've got no guarantees that the things that the member function are calling are thread safe. So, because these are all allowed or would be allowed through these constructs, that's problematic. The other problem is that because we unwrap the synchronized value, we get this point where we can actually just take the address of the reference to that internal object, and then we can just throw it out of that safely locked area to some other thread, some global string, and then it could be using it while another thread comes along and tries to use it as well. So we've really got a problem that it can escape that bounds. And also, safe pointers or smart pointers are supposed to be safer, but imagine that you take the address of a unique pointer and then you hold on to it, and then you move the object into a thread, so that's fine, but then you can just use that pointer still. That's still a valid object, it's just the unique pointer has been moved to somewhere else. So we have all these problems. We've got nested pointers, this pointers, global pointers, leaked pointers, and so on that kind of don't really make this a fantastic solution. We're a bit safer, but we're not safe. How far have we got? Well, we've used an unenforceable safe thread class. We've used a non-standard synchronized value class. And because it's not standard, we've had to add our own type trait for it. I didn't really show it, but we've done a lot of fighting with the compiler as well. Mainly through template instantiation and trying to conform to those sync and send concepts or type traits. And I sort of feel this is similar in spirit to what Rust developers call fighting the borrow checker. You're basically trying to nudge your code around in order for it to be able to prove to the compiler that you haven't created data races or used incorrect constructs. We've also added a lot of overhead to the code. We've got automatic reference counting and mutex locking everywhere. So we've got a solution that isn't bulletproof, it's not beginner friendly, and it's not default. So I'm not sure if I could describe this as a win. But as I said, it's a useful exercise to see where the problems are. And if we compare the code on the left with Sean's circle example, we can see there's actually a lot of similarities. So the first thing is that he has to copy that shared data into the thread as well. And we have to create a copy using auto. The main difference is he does have to lock the data in order to write to it. But because Rust has borrows and he creates a borrow to the string, there's no opportunity for that borrow to leak out. So the borrow checker will stop you kind of leaking that reference or pointer out, whereas we don't have that guarantee in C++. Now, I'm not a Rust developer, but I took Sean's circle code and gave it to an LLM and said, can you give me a Rust version of that? And it said, sure, I get the gist of what's going on here. And it did it. I checked it compiles in Godbolt, gives the same results, and it works, right? You can see it's basically the same line for line. But I said, that doesn't look like idiomatic Rust. Can you give me a version with borrows? And it said, yes, I can. And here's how I changed it. Basically, it removed the automatic reference counter, or the shared pointer, if you will, and replaced it with borrows and made a bunch of other changes to kind of adhere to that. It also said this is better because it's more efficient, it has no atomic reference counting, it's also cleaner. We can see that the code's a bit shorter, but we still get the strong safety through the Rust borrow checker and mutex locking. And it's because you could do this kind of final transformation with Rust to avoid that reference counting, to use borrows to get kind of strict lifetime semantics, that I think without a way to properly express lifetimes in terms of borrows, relocations, drops, we just don't get that same level of safety and performance in C++. And it's that and performance that I think will end up being critical. But as I said, if we go, it's a useful exercise anyway. If we go back to C++ and go through those problems, we can start maybe seeing what the language needs in order to address those holes. So let's look at nested pointers at the moment. Now, a feature coming in C++ reflection actually enables us to solve this quite straightforwardly. So remember we had this node example and it contains pointers. So at the moment, this code would slip through a synchronized value to a node because a node is, copyable. But we really want to reject that. And the other thing that we want to reject is something like a capturing lambda where it captures an unsafe object or a this pointer or any kind of raw pointer, basically. Now, because lambdas are effectively just objects of types, we can just treat them as types in reflection. And this is what the code, that same kind of type trait that I wrote earlier would look like using reflection. It's written a bit differently, and it actually follows the form of that flowchart I wrote a lot more closely. So you first check for non-member function pointers. So if it's a pointer and it's a function type and it's not a member function pointer, then you can return true. So that's the check that we did at the end last time. Then you check for L-value references or pointers of arrays or anything like that. If it's arithmetic type, like a scalar, int, float, then that's okay. And then the real magic comes when we get to ask if it's a class type. And if it is, we can then iterate over the members and check that they all conform to this isSendType function as well. And then we use it in a very similar way, except for we just create our concept and our trait that derives from as isSend reflection of T. And we could add in our isSyncV check as well. So now we can see if we use reflection, our static assert for isSend of the node, then that's now getting rejected. And similarly, any capturing lambdas we can now allow because we don't have to reject them out of whole cloth, but we can just say if there are any references or pointers that it's capturing, then we reject those. And similarly, we can get kind of more complicated by saying if we're trying to pass a member function to the run function or a this pointer, that kind of thing, then we can reject those as well. So we've kind of solved the first two problems just by using reflection. So let's look at the next thing, which is where we're able to steal the address of that internal object. And as I mentioned, Rust doesn't let you do this because you have to take effectively a borrow to that object in order to use it, or at least the borrow checker will stop you creating additional borrows. Now, the following section uses a lot of things that are yet to come in C++. I say the main reflection proposal is accepted. As far as I'm aware, it basically just needs rubber stamping in the next meeting. When I wrote all this, the code injection with token sequences was looking very hopeful for C++ 26, but apparently the meeting a couple of weeks ago, this has been pushed to 29. So, what I'm talking about should be possible, but perhaps in a few years. And I've also used Herb's metaclasses proposal just because it gives really nice syntax to what I'm showing. Although, as Herb states, it is just syntactic sugar. You can write everything without the metaclass proposal. You just effectively do its free functions. But it's the ideas that I'm talking about here that I think are the most useful thing. So imagine we're going to start with instead of having a string object before, we've got a custom class, which is a person. And a person just has two names, first and last name. So two distinct data types. Now imagine we want to make this into an object that's free from data races, a thread safe object. Could we just add a property, like a meta class to that class that says, I want this to conform to the @synchronized meta class. Now, what that meta class would do is effectively a transformation that would wrap that class into an internal person reputation. I've used $_ because it's compiler generated. It's probably not okay in the standard, but it serves for today's purposes. And then you would create a synchronized value to that original person on the left-hand side of the screen. And then you have a handle to that, which is person underscore. And then all you're effectively doing is reflecting over the original class function declarations and constructing these apply lambdas using token generation and forwarding on the arguments. So you can do it when you're capturing arguments and also when you're not, and just returning values as well. And because we're doing generation here, we can also say that this is now sync. So anything that conforms to the synchronized meta class is sync because we've made it free from data races. Now, I'm not going to show all the reflection code for this because it's quite long, and the compilers that implement this stuff have kind of got out of sync with what the current proposals are. But if you want to look at Herb's talk from CPPCon, he kind of goes into this meta class idea in a bit more detail. Now, this synchronized meta class seems a bit heavyweight, token generating lambdas and things. What if we just had mutex as a meta class? Now we just do the same wrapping as we did before, but we add a class member mutex and then just lock it in all of our functions before we go on and call that function. And again, we can generate the same sync type trait. Or we have a class that we know is mostly read-only. So we create a shared mutex meta class that just creates a shared mutex and then shared locks in your const functions and unique locks in your non-const functions. So that's would be good if it's mostly read-only. And you could do this with lots of different types of lock. For example, if your object is trivially copyable, you could use a Krill sequence lock, which is a wait-free on-write object, which is good for real-time code. Now, if we go back to our example and say, rather than the string passing around, we're passing around a person, how would applying these principles change the code that we'd have to write to use them? And it's quite a nice transformation, because now we just need a shared pointer to an object that conforms to the sync trait or concept, which person does because we made it happen. So you just have to pass a shared pointer to a person around, and then you can just call that object directly. So that's quite a nice first step. Now, to see the next problem, remember we could grab pointers out of objects and then hold on to them and then perhaps data race on them. And in our example, if we have a shared pointer, you can still get the pointer out of the shared pointer. So that's not particularly good either. We really want to abstract away the fact that there's a pointer there at all. Now, we can kind of do this by baking the shared pointer into the actual type that we're generating. So imagine we create an arc or automatic reference counting type, and then we do this same wrapping trick that we did before, but now we're wrapping that original person in a shared pointer. So that just gets copied around everywhere, and like a shared pointer would, and then we just forward on the arguments forward on the declarations as we did before. And now we can say that this is send if the internal person representation conforms to the sync trait. Now, that kind of sounds like a bit of a mouthful, but it will become clearer in a second. So this may seem familiar, and it should do if you're familiar with Swift at all, because classes in Swift are reference counted types. They're effectively arc or automatic reference counted types. So these two, this bit of Swift and this bit of C++, are kind of functionally equivalent. Now, the idea of metaclasses is that you can also implement or apply them one after the other. So if you apply the mutex metaclass first and then the arc metaclass, you effectively get a sync object wrapped in a send object, and the whole thing becomes send. So now, rather than having to write a shared pointer to a person, you just have a person. Now, this is safe to transfer between threads, and it's data race free. The other cool thing is, because it's not a smart pointer anymore, you don't have the arrow operator. You just use dot, and that's another kind of cool thing. Now, just to kind of make this a clean wrap up of an automatic reference counting type, the one additional thing that Swift has, and it's really one of Swift's only kind of not so great safety areas, is that it's possible to create cyclic references which might cause memory leaks because references in Swift are strong by default. So to break these cycles, you need a weak reference. And weak references are effectively observing references that get nilled when the last strong reference is destroyed. And these must be checked before dereferencing. So you kind of construct them with the weak keyword, and then you have to use the question mark operator to only do the following kind of dereference or member function call if you have a valid strong reference. And we can model that in C++ quite nicely with code generation. We can just generate an internal weak ref class that just takes a weak pointer to the shared pointer that lives in the generated person. And then when we want to get that, we really need a live person, a valid person. So we'll get an optional person because, of course, all the strong references may have been destroyed, in which case we'll get null opt. And we use it in a very similar way. We create a person weak ref, and then we can assign it from a strong reference, and then we just have to get the person out of that and then use it. And you could use the monadic extensions to optional as well. So that's kind of how we would model Swift classes. But Swift has a different data type called structs, and these have value semantics. Now, where you have two variables of a Swift class that have an underlying shared representation, two instances of a struct in Swift have distinct objects. And these have the interesting property that they're sendable implicitly if all their members are sendable because because they can't be shared. So things like scalar, POD types, objects that are self-contained like string because they're just a pointer and an extent. They don't kind of leak out into anything else. They're sendable as well. And they can be implemented somewhat more efficiently using copy on write rather than just kind of copy every time a new reference is made to it. So in Swift, you create a struct to have these semantics. And although we have a struct in C++, which looks similar, creating a new person would just create a copy of all of the data members as well. We create a copy of the whole object. So imagine we want to model this copy on write. Well, imagine we wrote a meta class to do that. And then we would effectively generate this optimization by holding the internal person in a shared pointer as we do before. Remember, this is only going to work if the type is copyable, though, or copy constructible. So we keep the internal object in a shared pointer, and then we can just use it through const functions. But when we have the first non-const function, if there are any other references to that internal representation, we need to create a copy. So if the use count is greater than 1, then create a copy of that object, and then we can safely write to it because it won't be shared by any other persons. And we can sort of forward up then the send trait, because if the internal person is send, then this copy on write object will also be send. Now, this kind of looks complicated because it feels like there should be a data race here because each person has its own shared pointer instance, but that internal like person underscore is never shared between different persons. It's only the thing it points to that's shared. And as soon as a non-const function is called, a unique copy is made. But this is fine because it's only a read. So that dereference of a person at the end there, that is just a read. And if other threads are reading that same person at the same time, that's fine. It's only when you come to write to it that now we have a distinct object. Now, there are some holes in this. It kind of looks too good to be true because it sort of is in C++. This only works if you only create copies of these kind of metaclass derived types, like these new persons that we're generating. As soon as you create a pointer or a reference to this, then you have problems. Now, send enforces this when you're passing to a thread because it has those checks to make sure it's not a pointer or a reference. But there are a few other tricks we can try to avoid this. We can delete operator new, which will avoid these things getting created on the heap, so they can't be stored in smart pointers. And we can delete operator ampersand to avoid taking the address of these objects. But unfortunately, there's no way to stop references in C++. You can still take a reference, which is effectively a pointer. And if you combine these objects, then say you have an enclosing type that has a person inside of it, and then you take a pointer or the address of that parent type, then you effectively are taking a reference or a pointer to the person, and therefore all bets are off. The only way I can think of around this is you'd have an additional trait to say this person is non-addressable, and then you'd need the compiler to check all of your types that contain these non-addressable types you never take the address of. So, and I think that kind of viral checking is not really, it's not a pleasing strategy for the committee. So maybe some thought needs to be done on that. But I mentioned we'll circle back round to high-low, and this is where we do, because high-low effectively gets its thread safety from avoiding shared state, and it does it by effectively creating, by effectively being similar to Swift, but without the reference types, without classes. Everything is effectively a kind of copy on write object, but more efficiently than a copy on write. Objects are mutable effectively within a function, which gives you local reasoning. You know that those objects aren't going to be referenced by another thread or concurrently referenced by another thread outside of that function. And as I said, this is similar to Swift with only struct types. But I imagine it's not implemented as copy on write all the time. There's probably ways the compiler can kind of prove that an object just take a pointer to it. But we're kind of trying to model those heuristics in C++. Okay, so that's sort of the end of the sync and send section. So if we do a quick review, we introduce this idea of send, which really introduces an isolation boundary between threads, and objects can only be copied or moved between them. And a sync trait allows the compiler to tells the compiler that an object is data race free, and therefore it's implicitly send if you can in some safe way get a reference to it across. And these traits need to be checked recursively for all members of types. And C++ today can't do this, but we should be able to do it with C++ reflection. We've also seen how lifetime safety is kind of inherently intertwined with thread safety. So we use shared pointers to kind of get around reference semantics, but that also gives us lifetime safety guarantees because there's no way to kind of dangle those references anymore. Other languages like Rust and Circle have borrow checking or mutable value semantics. What we really need to do is encapsulate pointers in value types to ensure that they're not exposed to abuse, so their addresses don't leak out. And hopefully C++26 reflection would and possibly metaclass generation can make this simpler. Now, I know there's lots of limitations to this because it's not the most efficient. We've got mutex wrapping whole class members, not individual members. And remember, in that person, we had a first and a last name. Well, they could be independently locked. We've got problems with inheritance. What if you try and inherit from an object that conforms to one of these metaclasses? I don't know. What if original functions were virtual and you derived and overrode those virtual functions? Then there's no way for these mutex locks and things to be inserted. Perhaps derived classes could possibly inherit the metaclass, so they kind of traverse down with it. Or maybe it would only work on non-virtual classes, or perhaps you just can't derive from these metaclass generated types. This is very early days for this kind of stuff. It's also, there are very few compilers where you can test things out, but I think it's just interesting to kind of poke around with these ideas to see what might be possible. We really need implementation experience. There are a whole bunch of concerns as well, because this bakes data race safety and lifetime management into the type. And this probably isn't suitable for every use case, because we pay a performance cost for the simple use cases in single thread, for example. And it's also, we know it's not the most efficient because borrow checking is, that's really just pointers, right? No reference counting, no smart pointers, no indirection, any of that. However, this has proved to be really successful in some languages like Swift. And these are already patterns that people use a lot. Like we have value types that wrap smart pointers and intrusive smart reference counting, things like that. These are well-known patterns that get used in C++. I just think that C++ can add a few little things in order for us to make these a lot easier to use, to write our own abstractions to encapsulate these ideas. The big argument that people, will have against this is that it's not C++ because it contradicts the don't pay for what you don't use idea. Now, we've talked a lot about sync and send, and I am running out of time, so apologies for rushing through this next section, but hopefully it will be more straightforward now. So Swift actually has a third data type called actor. Now, it's a reference type like class, except for it serializes data member accesses onto a dispatch queue or kind of worker thread. And because everything is serialized onto that thread, it's inherently free from data races because there are no concurrent reads and writes. And it also makes those accesses asynchronous, so you have to await the results. Now, I think we can model this with a meta class in C++ by just having an actor meta class, which would do a similar transformation like we did before. So we have this internal person that we're wrapping. But now what we're going to do is use the new senders feature in C++26, and we're going to just reflect over the function declaration and kind of put that, construct a lambda with that declaration, and then create a sender and run that on a scheduler. And if that scheduler is just a static thread pool with just a single thread, then any access that's done through these through that same scheduler will effectively be serialized and be thread safe. So if this was just a global thread pool that any of these actors used, all of those data races, all of those accesses would be data race free. Now, we could do a sync wait here to wait for the sender to return and then unwrap the value and return it. And we can do the same thing if we need to accept an argument, we can just copy it into the lambda. And this is a bit of a messy example, but I hope it illustrates the idea here that we've got a main thread, which is this green bar at the left-hand side, and then we call a function on this person, this actor, and then we start another thread and call a different function, and we've just got a reference to this person here, but that's the purple thread, but all of the actual data member accesses are done on this third red thread. So we could actually simplify this, because rather than just doing a sync wait, which is kind of pointless, why don't we just use a mutex? We could use a task, which is effectively just a container for a coroutine, and then we can co-return, co-await the sender and package that into a task. And now we can co-await the result. So we've turned this into a task-based coroutine. And we can actually simplify this a bit more, because we can just co-return, co-await the sender that's returned from running on this scheduler. And we can see that the bit that we have to reflect and generate is actually really small now. It's effectively just this lambda. And the code that we write and how we use it is now almost identical to Swift, which I think is pretty cool for just a small amount of work. Now, there are some problems with this kind of initial version. For example, imagine you're passing a string view, that's effectively just a pointer, and if you capture it into the lambda, we've got no lifetime guarantees that that's still going to be in existence after the function has been returned, because remember, it's now asynchronous. So maybe we want to assert that the arguments conform to the send trait that we did earlier, or maybe we could reflect on the lambda type to ensure that it's send, or maybe we could do forwarding of the arguments like we did before with the safe thread class. So, at some point we need to check that there's some kind of safety as it passes this isolation boundary. There's a whole bunch of optimizations we could do as well. So at the moment, we've just got a single thread that all actors are running on, but maybe we could, probably if we made one per type or, per instance, there's probably too many threads. But imagine we could use annotations for reflection, which I think we'll probably get soon. And then you could create different tags for different pools. So you could create a low priority tag, which would just, I don't know, run a really low priority thread. And maybe you could create different scheduler types. So a main actor could use a run loop that your main thread dispatches. So now any accesses on that actor are actually run on the main thread. So data race 3 free in relation to the rest of your main thread. So a whole bunch of ideas there. And there's one more optimization that you can do, because if we have functions that call other member functions, we don't really want to kind of schedule everything onto onto that thread. We could just check that the thread ID of the currently executing thread is going to be the same as the thread ID that it will be run on. Then we could just package that into a coroutine straight away. Now, I've nearly finished, but there is kind of one section that I wanted to end up with. And I've talked a lot about features that are coming in C++, but I did want to think about, is there anything practical that we could do today to improve thread safety in C++? And unfortunately, I think we have to listen to those original Chromium developers and say, well, it's probably going to come through runtime checks. Now, there is a solution for detecting data races in C++ at the moment, and it's called TSAN. It's only available in Clang and GCC, though. It doesn't have any Visual Studio support that I'm aware of, and it requires kind of separate running. You have to build specifically for TSAN. It's not just something you run on your normal everyday builds. And it's also mutually exclusive with other sanitizers like ASAN or UBSAN. And because it's, as we'll see, it's quite heavyweight, I sort of feel that it normally gets run on tests, and therefore it's only as good as your test coverage. Now, fuzzing can help to improve that your test coverage is good, but it's not quite the same as using an application kind of really. It's also extremely heavyweight. It's about 5 to 15 times slower execution time, 5 to 10 times increase in memory usage, and 2 to 3 times increase in binary size. And you also get a moderate increase in compilation time. Maybe even just for that reason alone, people won't use it on their kind of general engineering builds. But what TSAN does is it really detects data races, so a read and a write concurrently on a memory location. Now, if you don't have any readers or writers and then you start a read or a write, you don't have a data race. So we're really only interested in this area where you have an active reader or writer already and what happens at that point. And although TSAN works on memory, which is really where the data race is happening, you can sort of take a step back and say, well, let's just look at a scope to see if there are any concurrent uses of that scope. So we're going to say, if there is an active reader in a scope and another reader comes along, that's fine. We're going to allow that. But if anything tries to write during that time, then we're going to consider that a data race. So only this area will be safe. So what we want to do is effectively store some state to say, is a scope being read or written to? And we could do that with a simple struct that just checks the number of readers and whether there are any writers. And then we could have two functions, a read started and a write started. And then we increment the number of readers on a read start. And then we check if anything's writing. And if a thread is writing, then we just terminate, abort, or whatever you want to do then. And if you're starting a write, you want to say that I'm the one now writing, and if I didn't get to start writing because something else was writing, then again, you have to kind of bail out and say a data race was detected. But if you do get to start writing, then you check the number of readers and say, well, if there are any readers at this point, then I know there's a data race as well. And at the end of that scope, you just decrement the number of readers or set your writing flag to false. And of course, you can wrap this up in a nice RAI class to just insert a kind of scope check. Now, we've done a lot of meta classes. Why not one more? Imagine you just wanted to add this really easily to your classes. You would just add this meta class data race checker. I said this was going to be used. It was something you could do today, obviously not with meta classes, but you could insert that data checker and then what I'm going to show you next manually. So you could insert that check state manually and then the scope check in your const functions for reading and non-const functions for writing. But of course, if you had a meta class to do that, it's just going to do it without you having to remember to do it. So there's that check state and the scope checks accordingly. Now, I thought, well, this is nice for your own code, but is there any way that this could benefit us in terms of the standard? Now, the standard actually does talk about data race safety in terms of its containers. And I'm not going to read all of this out because it's a bit wordy, but basically it says that all const member functions can be called concurrently by different threads on the same container. So what that means, and it also stipulates that there's a few functions like begin and end are treated as const. So what that means is that those are data race free. That's the contract that the standard container is to be used under. So I thought, well, maybe we could just apply this idea of creating this checked state member and then add all of these to the standard library. And then you would effectively have relatively lightweight data race checking on the standard library. And because that's a very low, usually low level types, if you get data races in those, it normally means that at some higher level, you've constructed your threads or passed an object around that shouldn't have. So, detecting on some small bounds can give you actually really good data race checking. But of course, adding a member to the standard library functions classes is going to be an ABI break. So is there a way to do this without an ABI break? And actually, Herb wrote a blog post at the beginning of this year with the idea for tracking union types. But in order to be able to track union usage without an ABI break, he created this idea of extrinsic storage, which is essentially just a map of some custom data. Now, he uses it to check what type is being used in a union. I thought, well, this could get used by checking, by storing one of these check state objects. And all you have to do then is create one of these objects by passing a pointer to the instance that you've created. And then when you finish with it, you just call this onDestroy function. Now, the cool thing about this extrinsic storage type that he created is that it's basically wait-free all the time. The only time it becomes lock-free in relation to different calls on it is if you have to kind of allocate new pages to the container, but there are ways around that as well. But what you could effectively do then is, without adding a data member to the class, you just create a scope check of a read type in a const function, and then you use this data race registry get state and pass the pointer. It will create that data if it needs to, or you could do it in the constructor, and then just start using it, which I think is quite cool. I had std terminate, you could use std abort, but what actually if it was just a contract violation? So we now have the ability to specify in code the contracts of classes, and we know that this is a contract of the standard library containers. So we can just use a contract assert here to say, well, we can only start reading if there are no writers. And we could write them in line like these contract asserts, or we could phrase them as preconditions, because that's what they are really. So you could just state them nicely up front. And then your custom contract violation handler would get called. You could log it, continue, whatever your custom behavior, nicely kind of baked into the same system. So that's just kind of one little idea I had at the end. Now, this is limited because it works on kind of function entry exit, not memory. So therefore only functions that return references or pointers or expose their internal memory, this is not going to really work well on. But actually I do think it will work in a lot of cases. And I haven't shown member function delegation. So if a function calls another function, but in the SCL library, I have implemented that. You basically have to just keep track of the thread ID or the stack pointer and then compare those when you get a data race flagged. But I do think this could be used to check container contracts. And I think it's going to be a lot more lightweight than something like TSAN. But we will still have to test with TSAN. This wouldn't be a replacement for it. Now, finally, I've just got a minute or two left. I just wanted to kind of wrap things up by saying, what is the current kind of outlook for bringing thread safety to C++? And to be honest, the only thing I could find is this long-standing profiles paper by Bjarne, where there's this relatively small section that I've kind of poked fun at a bit before for being very brief, but it does say, you know, this is just the start of an idea. But it does have some interesting things we can draw from it. So the first thing is that he says, look into the possibility of statically detecting aliases in more than one thread to mutable data. With the current type system and pointers and references that C++ has, I think this is going to be really difficult. He also says, mutability, prefer to pass and keep pointers to const. Now, I showed really early on that I just don't think you can do that because of the aliasing rules that C++ has. Like you could pass a const pointer to something, but it doesn't mean that something else can't mutate it elsewhere. You'd have to do a lot of tracking, which I think is going to be difficult. And then finally, he does say this, which is statically detect if a pointer is passed to another thread. Now, this actually, I think, is sound. This, to me, seems to be the start of a notion of an isolation boundary. Like, if we could get something into the language to actually say when something is going to be executed in another thread, then that's the kind of the first building block I think we need. So, in conclusion, I think C++ needs a way to identify these isolation boundaries, i.e. some kind of send trait or concept. And this introduces strong aliasing and lifetime requirements so objects try and pass this barrier. And I just don't think this is compatible with existing pointers or references. Now, reflection can help us write in the styles of other languages which have better thread safety because we can kind of safely encapsulate those pointers. But for C++ performance and conforming to the don't pay for what you don't use, we'd really need borrow checking. And I think Sean Baxter's Safe C++ paper and his webinars explain that really well. Like if you want to have C++'s pointer or reference-based performance, but a safe version of that, you are looking at borrows. There really is no alternative. So I hope you've enjoyed this kind of journey of my kind of investigation through thread safety. I'm going to head to GatherTown now for any questions. The slides will be up on my GitHub along with that SCL project you can find. And hope you've all enjoyed it. Thanks very much.